Okay, so the next one is exercise 11. Here the setup is the usual one that we have with field extensions, that is f is a given field and E is an extension of f. Also, we are considering a polynomial fx over f, and an automorphism is given. An automorphism of this extension E, which has the property that it leaves every element of f fixed. That is, it does not change anything of the base field f. Then we have to prove that this map phi must take a root of fx lying in E to a root of fx in E. That means if we find a root of this polynomial fx in the extension E and apply the map phi on that, then the result is again a root of fx in E, of course, because phi maps E into E. So let us now see the solution. So we assume the explicit expression of the polynomial, say it is alpha naught plus alpha 1x plus alpha 2 x square, like that, alpha n x to the power n, where the alpha is are coming from the base field f and n is a non-negative integer. Also, let alpha belonging to E be a root of fx. That means if we replace x with alpha, here we are going to get 0. Then then 0 is equal to 0 phi, because phi being an automorphism is a homomorphism, so it maps the 0 element of E to itself. Now we can replace 0 with this. Since alpha is the root of fx, phi, the phi image of this. Looking at this expression, if you feel that this there is a chance of confusing this alpha with the coefficients alpha, you can use some other symbol here also if you want, say beta or maybe some English alphabet. But now, using the fact that phi is a homomorphism and hence it respects both addition and multiplication, we have next this alpha naught phi plus alpha 1 phi times alpha phi plus alpha 2 phi times alpha phi square plus alpha n phi alpha phi to the power n. Okay. Now we use that other part of the hypothesis that this automorphism phi fixes every element of f. So because the coefficients, the alpha i's are coming from f, so then none of them will change under phi. So we have something like this: alpha 1 alpha phi plus alpha 2 alpha phi square plus alpha n alpha 5 to the power n, and that is nothing but f of alpha phi. So f of alpha phi is also 0, and hence alpha phi is a root. Is also a root of our polynomial. So that is the solution. Next, prove that this extension of f obtained by attaching the cube root of 2, where f is the field of rational numbers. This extension has no automorphisms other than the identity automorphism. Okay. Solution: let phi be any automorphism of our field, our extension field. Then phi being an automorphism, phi will fix two elements. Phi will fix the rational number 0, and phi will also fix the rational number 1. These are actually integers. Then 0 phi is equal to 0 and 1 phi is equal to 1. Let us recall why this is the fact though. 0 phi is equal to 0 because phi is a homomorphism of the additive group that we have in the field. Just like that, 1 phi is equal to 1 because phi is also a homomorphism of the multiplicative group of non-zero elements in a field. So that is why we are getting these two things. This implies this implies R phi is equal to R for all R belonging to F. That means these two equations can be used to show that phi actually fixes every rational number. Do you see how? You have to do it in stages. So the thing here is this. Using this equation or this fact, by induction, you can prove in an extremely straightforward manner that n phi is equal to n for every positive integer n. Then, using the fact that phi is a homomorphism, phi respects addition and is a homomorphism of the additive group of the field, using this fact along with this phi fixing 0, that thing, you can prove that here n is a positive integer. You can also prove this, that phi actually fixes all integers. But if phi fixes all integers, then since phi is a field automorphism, every rational number is a quotient of two integers, where the denominator of course is non-zero. So this follows from the fact that phi is a field automorphism and phi fixes all the integers, so neither m nor n changes under phi. That means we get back r. So that's how phi fixes every rational number. This is extremely straightforward, so we can just simply conclude like this directly. Okay, so it turns out that phi fixes all rational numbers. But our field does not just have rational numbers. In fact, it's an extension of the field of rational numbers, which has some irrational numbers also. But now if it turns out that phi also fixes this element that we have attached or adjoined to f to get this extension, then actually phi will fix the entirety of this extension. Why though? Because recall how the general elements in this extension look. Recall that the degree of this extension over f, that is over the field of rational numbers, is 3. So as a vector space over f, this extension has a basis having 3 elements, and one such basis is this. Which means, that is, this is a basis, which means that the typical element or the general element in this extension looks like this: alpha naught plus alpha 1 times cube root of 2 plus alpha 2 times cube root of 2 square, where this alpha naught, alpha 1, alpha 2, they are rational numbers, that is, they are coming from the base field. Now we already know that these rational coefficients are fixed by our phi. Now additionally, if we can also show that phi fixes this cube root of 2, then phi will fix everything. That's what we now want to show. Okay. Now since this is Oh, but before that I need, okay, I need to write about the extension. Can I write like this? Yes. Note that this is an extension of f, of course. We just want to write things in such a way that we will be immediately able to use the result of exercise 11. That's why we are writing like this. Note that this is an extension of f such that the cube root of 2 is the only root in of the polynomial x cubed minus 2 coming from the polynomial ring fx. The other roots are non-real complex numbers. Okay, so let us first try to understand what we have written here. This is an extension of f that we can of course see, such that cube root of 2, this is the positive real cube root of 2, which exists, we know this from calculus or analysis. This is a real root, and this is the only root lying in this extension of this polynomial, which is a polynomial over the field of rational numbers. Why is it the only root? Because the other two cube roots are both non-real complex numbers, where one of them is omega times cube root of 2 and the other one is omega square times cube root of 2, where omega itself is a non-real cube root of unity. So that's why we have written the other roots are in C minus R, that is they are non-real complex numbers. But why is this, why are the other roots not lying in this extension? That is because this extension consists of only real numbers, or rather I should say all the elements in this extension are actually real numbers and none of them is a non-real complex number. That's because we have just now seen how the general elements in this extension look. So they are just all real numbers. Okay, so now if we apply the result of exercise 11, then what does that say? It says that if we apply any automorphism to a root of such a polynomial, then the result is again a root of that polynomial. So if we apply our automorphism phi to this, then we should again get a root of this same polynomial, and that will also lie in E. This is the E here, the extension. But the only root available in this extension is cube root of 2 itself, so we are going to get that same thing. So we write like this. So by exercise 11, Thus, phi fixes every element of i.e. phi is the identity automorphism of this. So that means this has only the identity automorphism. Its automorphism group is the trivial group. Okay. Next, using the result of exercise 11, prove that if a complex number alpha is a root of the polynomial px having real coefficients, then alpha bar is also a root. The complex conjugate of alpha is also a root of p of x. So you understand that we just have to find the appropriate automorphism in this case of the field of complex numbers. Solution: we know that the field of complex numbers is an extension of the field of real numbers. Also, the map phi from C to C defined like this: z phi is equal to z bar is an automorphism of C. that fixes every real number. So here we are just going on stating things without actually showing why they are true, but it's extremely straightforward to show these things. For example, to prove that this function is an automorphism, what is it that you have to show? You first of all have to show that this map is, well, the map is of course well defined, so that thing is there, but you have to first of all show that it's a homomorphism, a ring homomorphism. That means it has to respect both addition of complex numbers and multiplication of complex numbers, which come directly from the properties of complex numbers. That's because for two complex numbers z1 and z2, this complex conjugate of their sum is equal to the sum of their complex conjugates, proving that our phi respects addition. Similarly, we have this, proving that phi respects multiplication. Then you have to show that this phi is 1 to 1 and onto. 1 to 1ness of course comes from this. Say you take two complex numbers for which their complex conjugates are the same, then the complex numbers themselves should be the same, because you can then take conjugates of these conjugates, which will give you this. Outputs are equal implies that the inputs are equal, so the function phi is 1 to 1. What about ontoness? You take any complex number z, its inverse image under phi is z bar itself, the complex conjugate. So that's how phi is an automorphism. And why does it fix every real number? That's because you know that the conjugate of a complex conjugate of a real number is the real number itself. So that's why we are now in a position to apply the result of exercise 11. And also because our polynomial px has real coefficients, that means it is a polynomial in the polynomial ring Rx. So by exercise 11 alpha bar, so it's given that alpha, the complex number alpha, is a root of px, the real polynomial. So the image of alpha under phi, which is alpha bar, will also be a root of px. And that's how the solution ends. And an exactly similar one is the next one. Using the result of exercise 11, prove that if m is an integer, which is not a perfect square. Yeah. Which is not a perfect square, and if alpha plus beta times root m, where alpha and beta are rational, is the root of a polynomial px having rational coefficients. In the previous one we had a polynomial with real coefficients. Here we have rational coefficients. Then alpha minus beta times root m is also a root of p of x. And from the previous exercise, from the previous solution, you know what you have to do. You just need an automorphism, and from the two given roots we know what automorphism we are seeking. So I am not going to write a formal solution, I will just simply give you the automorphism, leaving the verification of the fact that that mapping is an automorphism also to you. So the map that we have here is just simply this. Because these specific numbers are given roots of px, so let's just write a plus b root m, a minus b root m. Because it's given that m is not the square of, m is not a perfect square, m is not the square of an integer. So root m, this number, root m may be a complex number also which is not real. That will happen when m is a negative integer. Note that it's not given in the exercise that m has to be a positive integer. The only thing that is given is that it's not a perfect square, it can be a negative integer also. So in general this root m is a complex number whose square is n. So as a complex number, it is an algebraic number of degree 2, and this degree 2 comes from the fact that its square is a rational number which is m, but the number itself is not a rational number. So this is a 2-degree extension of the field of rational numbers Q, and the general element in this extension looks like this, a plus b root m. Why? Because just like that previous case, that cube root of 2 case, as a vector space over Q, this space has this basis. That's why the general element here looks like this. So what we are doing is that applying phi to that element means having this one, a minus b root m, which is also again in this extension itself. And you can clearly see that this is a well-defined map. However, why is it well-defined? That's because for a given element in Q root m, these a and b are uniquely determined. In other words, what I am saying is that if a plus b root m is equal to a prime plus b prime root m, where a, b, a prime, b prime, these are rational numbers, then a is equal to a prime and b is equal to b prime. Keep in mind that you have to actually show this, otherwise you cannot work with this function, because in that case you won't know whether it's well defined or not. It turns out that this is true, but you have to show this. Before showing anything else that may be true about phi, you have to show that it is well defined. Then you show that this phi respects the addition, which is rather easy to show. Then it respects multiplication, which is not as straightforward, but it can be done. And then you also show that phi is bijective, so it will then be an automorphism. One more thing that we need phi to have is that phi fixes every rational number, which it does, because any rational number r is of this form. So according to the definition of phi, it will just be this, which is nothing but r itself. So r gets mapped by phi onto r itself. So then you can just apply the exercise 11 result and have this thing. And also keeping in mind that our px, of which this alpha plus beta root m is a root, is a polynomial over the field of rational numbers, and this is an extension of Q. So the result of exercise 11 is applicable here, and that will just give you the solution. So please write the actual formal solution yourself. So I think 2 or 3 more problems, exercise problems, are left in this set, which we will complete in the next field theory update. So I am ending things here today. If you want to say something about these things, you can use the comment section below, or you can mail me. My address will be there in the description. And tomorrow, have we gone through Galilean's ring theory? I don't remember exactly what we went through on the last Saturday. So accordingly, the next thing will come. Either it's Lie or Galilean. Whatever we did previously, we are going to do the next thing. So with that, I end today's video. So see you tomorrow with either Lie or Galilean's exercises. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.